This video includes several more examples on solving quadratic equations using the quadratic formula. And all three of these equations are going to have a different aspect to them that makes getting started a little bit more challenging than usual. For example, clearing fractions or clearing decimals. And so we are going to go ahead and use the discriminant approach, the b squared minus 4ac approach, and then put it all together with the quadratic formula. So let's go ahead and get started. So this first equation, the little curveball that we have on this one is it's certainly not in standard form. And we have to multiply some polynomials to get the equation in the right format to use the quadratic formula. So we're going to use the distributive property. So I'm going to go ahead and rewrite the equation to solve. And we know that multiplication distributes across addition and subtraction, and that holds true for not just the real numbers but also polynomials. So there's your distributive property pattern. You might also know this as FOIL, first, outer, inner, last, naming the terms that we're multiplying. So we'll go ahead and take that product. So we got x times 3x, that's going to be 3x squared, and then x times 2 is going to be a positive 2x, and then 1 times 3x, positive 3x, and then 1 times the 2 is 2. Carry down the 6x plus 3. Now we're going to go ahead and combine the middle terms here in our product. They're like terms, so we're going to get 3x squared plus 5x plus 2 equals the 6x plus 3. Now we'll go ahead and get this to be in standard form. If you remember the quadratic formula requires the equation to be of this form: ax squared plus bx plus c equals 0. So we just need to get 0 on one side of the equation and everything else on the other side. So that's going to prompt me to go ahead and move the 6x using inverses. And while we're at it, we might as well move the 3 as well. And we have to subtract these things from both sides of the equation. So since I'm using the additive inverse, I'm going to put a sum line in here and then see where that takes me. So we do get 0 on the right hand side of the equation, and we're going to get 3x squared minus x minus 1. So now we're ready to go ahead and calculate the discriminant. We have the equation in standard form for a quadratic equation. So in the a position is 3. Remember that a is the leading coefficient, so it's 3 in this polynomial equation. And then b is in front of the linear part. It's a negative 1. A negative x in that equation implies that b is a negative 1. And then c, the constant without a variable, is also a negative 1. So we can use that to calculate the discriminant. The discriminant is b squared minus 4ac. So we're just using that formula. This is going to predict the nature of the roots to our equation. So when you do the substitution, you put in a negative 1 for b, a is 3, and c also negative 1. And we just use the order of operations to figure this out. So we definitely apply the exponent first. So negative 1 times a negative 1 is a positive 1. And then we're going to multiply everything else to 4 times the 3 times the 1. So that product's 12. But you also have a negative sign on the 4. That'll cancel with a negative sign on the negative 1. So this gives us a positive 12. So we get 13 for the discriminant. So what that tells us is the two roots to this equation, they're going to be irrational. We're going to get two irrational roots out of this because the discriminant is not a perfect square. If we get a discriminant that is 0 or a perfect square, it means we're going to get rational roots. But since this is not a square, we have irrational roots. Now the discriminant is positive, so therefore the roots will not involve the number I. So we'll go ahead and run the formula now. Keep in mind, we're just thinking about this formula as we run through the rest of the solution. So always have this at your side so you can reference it. So here we go. We've already done all the hard work by calculating the discriminant. So x equals a negative of b plus or minus the square root of the b squared minus 4ac. That's going to be the discriminant, all divided by 2 times a. And so we just put all of those parameters in position. So a negative of b, that's going to be a negative of a negative 1. The discriminant is 13, and a is 3. And so we just need to clean this up as much as we can. So this is going to be x is equal to a positive 1. Minus a negative is the same thing as adding 1. We'll get plus or minus the square root of 13. There is no way to simplify root 13 in terms of radicals. So those are our two roots right there. So I'm going to write them out as individual roots, and we'll go ahead and while we're at it, do the approximations. So one root is x is equal to 1 minus the square root of 13 divided by 6. And we can go ahead and approximate that in a calculator. And then the other root is x is equal to 1 plus root 13 all over 6. And we'll do the same thing on there. We'll approximate with a calculator. So I have a scientific calculator handy. So when you type this into a calculator, you do need to be careful with the order of operations. We definitely need to start with the exponent. Remember, the square root, the radical symbol, is also an exponent. So we'll take the square root of 13 in your calculator. You'll get about 3.60555. That's a lot of digits we're not going to worry about. But then we need to make it negative. You should have a plus or minus key in your calculator. You hit the plus or minus key, and then this one is positive no matter what, so we'll add 1 to that. Go ahead and hit equals or enter, and then the last thing is to divide out the 6. So the first root is roughly a negative 0.434. I'm going to go ahead and round it to the thousandths place. So that's one of the approximations to the irrational roots. Now, this form of the root is exact. This is approximate. And we'll do the same thing on the other one. The other one's actually easier to type in because we don't have to worry about the plus or minus key. So we're going to take the square root of 13 first. Add the 1 to that, hit enter, or equals, and then divide out the 6 is the last thing. That root is going to be 0.768. Oops, got it backwards. 0.768. So those are the two rational approximations to the roots of this equation. And these are the exact roots. So if we can live in the realm of the exact, we can report these for our answers. However, if we're doing like an application or something like that, then it makes sense to do approximations. And potentially in physics, you might be doing this, and you can use significant figures rounding protocol to figure out how to write out these decimal approximations. All right, let's do another example. So this example just has an equation that's loaded with fractions. So we're going to go ahead and use the algorithm of clearing fractions on this one. So let me go ahead and write out the equation again. So you always have to do this, when you're doing your work and have a question written in your textbook or in Canvas. You have to write it in another location, so I'm kind of modeling that. Okay, so looks like we copied it correctly, so now we're going to go ahead and clear the fractions. I'm looking at the denominators. It's pretty clear what the common denominator is. The least common multiple of 2, 4, and 8 is actually 8. So we're going to scale both sides of the equation by 8 to cancel our fractions. But be really careful how I show this. So I'm going to even color code it. So I'm going to write the equation as we just stated it. And then what I'm going to do is multiply or scale both sides of the equation by 8. So that's the new part, scaling both sides by 8. And we know that multiplication is distributive, and so we're going to carefully figure this out. Now, if you're used to this algorithm of clearing fractions, you can do this without showing too much more detail. Potentially you can add another step that shows all the canceling, but I'm just going to go ahead and calculate it. So if we multiply the 8 times the 3, you would get 24, and 24 divided by 4 is 6. So that's one way to look at it. Or you can say the 4 cancels with the 8, leaving you with the 2, and 2 times 3 is 6. Either way, we're going to get 6r squared. And then 8 times 1/2 is 4, or the 2 will cancel with the 8, leaving you with the 4. So this will be a negative 4r. And then we multiply the 8 times the 3/8. The 8s will cancel, just leaving us with an 8. A 3. and then that's 0 on the other side. Now the one good thing about having 0 on the right hand side of the equation is it doesn't matter what you divide or multiply by, it's always going to stay 0. So now our equation is ready to calculate the discriminant. It is in standard form, even though the variable is not x. That really doesn't matter. We're still referencing the quadratic formula, so it still has the correct format. It's in the A position is 6, B is -4, and C is 3. So we can still do everything that we can do with the quadratic formula. So we'll go ahead and I'm just going to carefully list out the parameters A, B, and C. So A is 6, it's the leading coefficient in front of the squared part. Linear part is -4, or the coefficient on R is a -4, and C is 3. And so we'll use that to calculate the B squared minus 4AC, which we call the discriminant. Okay, so B is a -4, A is 6, and C is 3. And now we just figure out what this is using the order of operations. Okay, so we're going to get -4 squared is 16. Here, the negative sign doesn't cancel out, so it's going to be a minus. And then we got to figure out what this is. Well, 4 times 6 is 24, and if you triple the 24, we get 72. So we get 16 minus 72, which is actually negative. It's a -56. So our discriminant is negative. What that means for us is that the roots will definitely involve the number I, which we know is equal to the square root of a -1. So we're definitely going to have to deal with this in these two roots. So the roots to this equation are going to be complex conjugates of each other. And the other issue is with the 56. 56 itself is not a perfect square, so that's going to introduce the radical symbol, or square roots. So it's going to involve irrationality and the number I. So we have that expectation based on the result for the discriminant. All right, so let's go ahead and run the formula now. So we have not x, but r equals a negative of b plus or minus the square root of the discriminant all over 2a. Just referencing the quadratic formula there. Okay, so we'll put everything in. A negative of b, that's a negative of the -4. The discriminant is a -56, so we'll have to do some simplifying there. There is a way to simplify that in terms of radicals. And then the denominator is 2 times a, so a is 6. All right, we'll simplify this a bit. We're going to have r equals a +4, because the double negative there. A negative of a -4 is like a negative times a negative. Plus or minus, and then we're going to need to bring out 4 radical symbols here. So I'm going to factor out the -1, get the negativity out of the way. But then there is a perfect square that divides 56. If you look at your list of perfect squares, you'd find out that 56 is definitely divisible by 4. You can kind of get that if you just add 4 to 56, you'd get 60. Add 4 again, you get 64. Yeah, we know for sure 64 is a multiple of 4. So definitely 56 is a multiple of 4. So we can factor out a 4, we'll factor out the negativity, and that's going to leave us with 14. And then the denominator is 12. So it looks like we'll be able to do a lot of reducing in these two roots. Even though the roots are going to be somewhat complicated, it will reduce. So we're going to have a 4 plus or minus, we'll take the square root of 4, it's going to be 2. Square root of -9 is the number I, and then we have the radical 14, and the whole thing is divided by 12. So we need to reduce this now. So in order to reduce this, we look for that greatest common divisor. 2, 4, and 12 are all multiples of 2. So the GCD of all three of these positions is going to be 2. And I'm just going to be real clear about this. So I'm going to do some factoring. So r is equal to, I'm going to factor out that 2. It's going to leave me with a 2 plus or minus just the I, root 14, all over 12. And now we're free to go ahead and cancel the 2 with the 12. So the 2 divides out with the 12, leaving you with the 6. And then we'll just write our roots. So r is equal to 2 plus or minus I root 14 all over 6. So those are the two roots to our equation. So definitely we get complex conjugates. And what we can do is we can write them out as a list if we wanted to as well. We can go ahead and just do this. You know, r equals, and then using set roster notation, one of the roots is 2 minus I root 14 over 6, and the other one is going to be 2 plus I root 14 over 6, and then close that off with braces. So that's the solution set showing our two complex conjugates that satisfy this equation. Okay, so that was a good example of clearing fractions, and also a little bit of involvement with that interesting number I, which is defined, remember, to be the square root of a -1. So the next example has the issue of decimals. So kind of like the last example that we just did, we're going to go ahead and clear out the decimals. And the algorithm for that is to multiply by a power of 10, like 10 or 100 or 1,000. It depends on how many positions you need to move the decimal point to get whole numbers. So if you look at this example, I only would need to move the decimal point one position to get the whole number 3, one position here to get 12, and one position here to get 14. So we can definitely just scale this by 10. So I'm going to go ahead and rewrite the equation. And I left myself some room to go ahead and multiply both sides of the equation by 10. So that's how we clear decimals. So we multiply by 10 and moves the decimal over once. This is going to be 3x squared plus, when you multiply the 10 to the 1.2, it's going to give us a whole number 12, and that's going to give us 14x. Again, multiplying by 1 moves that decimal one position. Now, you probably notice this equation is not in standard form. Standard form, we need to have everything on one side of the equation. You know, ax squared plus bx plus c equals 0. So we're going to have to move that 14x to the other side of the equation. And we're using the additive inverse for that. And then we'll rewrite that equation. So we do get 0 on this side, which is good. And then we're going to have 3x squared minus 14x plus 12. Now we're ready to go ahead and use the quadratic formula. We're going to calculate the discriminant first. That's probably the best approach to solving quadratic equations, in my opinion. So we're going to have a, b, and c. So a is 3, it's a leading coefficient, b is a -14, and c is 12. So the discriminant is the b squared minus 4ac. So we'll put that information in, do the substitution. So we have a -14, a is 3, and c is 12. And then we'll do what we can to simplify this as much as possible. Now, the square of 14 is 196, so the square of a -14 is also 196. A negative times a negative is a positive. But here we're going to get 4 times 3 is 12. We've got to go 12 times 12, so that's minus 144. And then when you do the difference of those, we're going to get 52. And always just make sure that you do get that discriminant correctly. You know, run through this multiple times just to be absolutely sure that you have that calculated. The discriminant is the most important part of the whole process. Now we're ready to run the quadratic formula. And just again, you always want to have this formula at your side so you can refer to it. This is what I'm doing. I'm looking at a negative of b plus or minus the square root of the discriminant all over 2a. So x equals a negative of b plus or minus the square root of the discriminant all over 2 times a. And then do our substitutions. We have a negative of the -14 plus or minus the square root of 52 all over 2 times 3. So again, we didn't really make any sort of claim about the roots yet because of the discriminant. But the discriminant is non-negative, so we definitely don't involve the number I in there. But the discriminant is definitely not a perfect square. So, 49 is a perfect square, 64 is a perfect square, so we're kind of missing it. It's in between those two numbers. So it's going to be irrational roots for sure. So x is equal to 14, because the double negatives, plus or minus, we're going to go ahead and start simplifying that radical 52 all over 6. So actually the perfect square that divides 52 is 4. And you find out 4 times 13 is 52. All right, so we need to clean this up a little bit, do a little bit of reducing. So we're going to get 14 plus or minus 2 root 13 all over 6. And then we'll go ahead and do our factoring and canceling here to simplify this. So x is equal to, the GCD here is going to be 2, so I'll factor that out. We're going to get 7 plus or minus root 13 all over 6, of course. And then divide out the 2 with the 6, or cancel the 2 with the 6. And we are left with our 2 roots. We get 7 plus or minus the square root of 13 all over 3. So those are our 2 roots. We can write them out as separate roots if we want to, and then go ahead and do the approximations. And it's very practical to do approximations, so I'm going to go and do that. So x is equal to 7 minus root 13 over 3, and then we'll crunch the numbers in a calculator. Or x is equal to 7 plus root 13 over 3. So those are the 2 roots to our quadratic equation. So when you are doing this calculator work, make sure you follow the order of operations carefully. So the first one's actually the hardest one because of the minus sign. But we'll take the square root of 13. That gives you about 3.6 roughly. And then we need to make it negative because of the minus sign. So you have a plus or minus key in your calculator. So now I have that negative. And then I'm going to add the 7 to it. And then go ahead and hit enter. That'll calculate the numerator for us. And then we just divide out the 3. And that gives us one of our roots. One of our roots is roughly 1.13, or 1 1300ths. So very practical approximation there. Now the other one is easier. Take the square root of 13 first. Remember, exponent first. And then add the 7. Get that answer. You'll hit enter. And then divide out the 3. And that one's going to be 3.54 if you round to the hundredths place. So those are rational approximations to our 2 irrational roots. And you can see this time I didn't really write it out as a solution set. But that's okay. You don't always have to do that. Okay, so this was 3 different type of examples of quadratic equations that just take a little bit of work before you can actually run the quadratic formula. We always got to make sure that equation is in standard form, and sometimes it takes some computing with polynomials, or clearing fractions, or potentially, like in this last example, clearing decimals. So I hope this video helps you with completing some of the other equations that you have to work on in the assignments. Thanks for watching.